Hi guys, I will be talking about heat, phase change, and heat transfer in this lecture. Let's get started. Alright, let's get started with heat. What is heat? It is a form of energy and it is basically measured in joules since the unit is, it's a form of energy, but heat can also be measured in calories. And the relationship in between calories and joule, 1 calorie is equal to 4.186 joules. All right, so this is the unit conversion unit for the calories and joules. And the letter for us, or symbol for us to show heat, is Q. And this heat can be measured in two different ways. Once you add energy to a system, it either changes the temperature, so this is slightly wrong, or it is going to also use not to change the temperature but to change the phase. So we will talk about this at the last slide. So heat is basically measured in two different equations, mc delta T if temperature is changing, if there's no phase change, but if there's a phase change, then it's going to be calculated by mL. And here, L is the latent heat, is basically how much energy per mass should be given to change the heat. And it basically depends on the substance. And C is specific heat capacity. And it is energy needed to change the temperature of the substance by 1 degree Celsius. So, for example, if you think about metals, and what else? Let's think. And plastics. So if you think about metals and plastics, and think about a hot beverage. If you have a hot beverage, what kind of material would you use? Would you use a metal cup or a plastic cup? So if you use a boiled water, if you put a boiled water in a metal, then that might not be really a good idea for you, because metals are going to have really low specific heat capacity. What does that mean? Since they have really low specific heat capacity, they are not going to need too much energy to change their temperatures. So if you give a little bit of heat to the system, or take away a little bit of heat from the system, the temperature will change automatically too fast. But for plastic, specific heat capacity is too high. What does that mean? They require a lot of energy to change their temperatures. All right, so basically, amount of energy needed to change the temperature is going to be known as specific heat capacity. And high specific heat capacity materials are going to resist to change their temperatures, and low specific heat capacity materials are going to change their temperatures real fast. And metals are the examples for that, and plastics are basically examples for high specific heat capacity examples. And that specific heat capacity basically depends on the material that we are using. And we're going to have 4 laws of thermodynamics, but they're not going to start from 1. They're going to start from 0. So 0th law, 1st, 2nd, and 3rd law. So 0th law says if you have 2 objects at the same temperature, and if you put those 2 together, then there won't be any heat transfer in between them. Because the key thing for heat transfer is temperature difference. So if A and B are at the same temperature, then once you put those 2 together, then there won't be any heat transfer in between them. And other description that they have for this is if A and B are at the same temperature and B and C are at the same temperature, then you can also conclude that A and C, they also have same temperature, but which is really a logical thing. All right, the first law of thermodynamics is about internal energy. And internal energy can be changed in two cases. You either do work in the system or you add heat to the system. So that means if you would like to change the internal energy of the system, adding heat is not the only option. You can also do some work on the system, and then that will also change the internal energy of the system. And what is internal energy itself actually depending on? I think we talked about it in the previous slides. So it is depending on basically temperature directly. There's no N, I guess. I think that was kBT, something like that. So internal energy itself basically depends on the temperature. So then what can we conclude over here? If you would like to change the temperature of a system, you either add heat or you do work in the system. All right, so that is basically the first law of thermodynamics. Internal energy depends on temperature directly, but if you would like to change that, then you either add or remove heat or you do work on the system. And the second law of thermodynamics, which will basically cover most of the questions on your homework too, is about if two objects at different temperatures come into contact, after a while, they're going to reach to the same temperature. Or any two objects with two different temperatures, so T1 and T2. If they are not the same, then what do you expect? You expect a heat transfer in between them. But what will be the direction of the heat transfer? High temperature to low temperature. This is the only way the heat is transferred. So the second law states if you have two objects at two different temperatures, they will exchange the heat. One will lose energy, the other will gain energy, but that lost and gained energy must be the same. And energy transfer is going to go from high temperature object to the low temperature object. And if you wait enough time, they are going to reach to the same temperature, which is called thermal equilibrium. All right, so that is the second law of thermodynamics. And if you actually make that statement, or if you want to put that in an equation, then release heat must be equal to absorbed heat. But since release means you are losing energy, so you basically have negative energy, and absorbing means you basically gain energy, so that's positive energy. So negative is not equal to positive, so that's why you add this negative in front so that they are equal in sign as well. So the magnitude must be the same, and the sign is basically made positive by adding another extra negative in front of it. So, and that doesn't have to be MC delta T equals MC delta T all the time, but this is going to be the case for most of the time. One, if the object is changing temperature during the transfer energy transfer, then we are basically going to calculate the heat by MC delta T. But in some cases, it is not going to use energy to change the temperature, but it's going to use the temperature to change the phase. So in that case, one will release the energy and the other will use the energy to change the phase. And in some cases, it is going to do both of them together. So again, this equation might not be the only version, but this is basically the one common version that we will be using during homework 12. And the final temperatures of two objects must be the same once thermal equilibrium is reached. To be able to do this, you need to wait for enough time. And the reason for the picture, basically, if I give you $10 I have negative $10 and you have plus $10. All right, so whatever I lose, you gain. So same thing for the energy as well. And the third law of thermodynamics is basically entropy, and entropy is the measure of randomness or disorder of a system. So I'm hoping that it's not, but probably your rooms are looking like this at this moment. So that is totally normal because this is the nature of the systems. Some systems tend to become disordered. So if you leave your locker, for example, if you do not actually spend time to organize it, it's just going to get messy. Just like anything else in the nature, they will tend to become disorganized. So, but how, or to be able to get them organized, what do you need to do? You basically need to do work, or you need to spend energy in systems. So that's why most of the time you probably heard about it, but once you are basically using your car, you basically, let's say $30 of like gas, but you basically use 20% of that gas. 80% of the gas is basically going to be moving randomly. So once you put the energy, you will only be able to get 20% of this gas molecules, or the energy that you are basically get only 20% of it. So 80% will be basically moving randomly, all right, because things tend to get disordered, not get ordered. All right, so this is basically the entropy, and this is the third law of thermodynamics. And the heat transfer rate. So if you have two different temperatures, and if you have basically put them in contact, then you are going to have a thermal conductivity in between them. But it will also depend on some of the variables. So heat transfer rate is basically H, and it is going to be depending on thermal conductivity of the material. So that's basically the molecular design of the object. So depending on that, it will have different rates. And of course, area. If you have a larger area, it's going to be easier to lose the heat, or it will be easier to gain the energy. So this is the reason why that you have this, you might think, stupid shape, but they basically try to extend the area so that the heat is basically distributed and taken away from the system faster. And delta T is the temperature difference in between the two different locations or two different systems that you're having the energy transfer through. And L, I don't know why it's given by L but not with, but L is basically the thickness of the material that you have over here. And Q is energy transferred. So there is, if you also want to include the time in it, then it will basically become so this heat flow rate will become heat energy and time division. So energy transfer will become Ka delta T over L times time. So it's going to include a time interval into the system. All right, so this is the rate, but this is the energy that you transfer in the system. All right, the last part, but the important part of this lecture is phase change. So once you add energy to systems, you have basically two options. If you're talking about like pure materials, let's say we are talking about ice. Once you add energy to the ice, what's going to happen first? It is going to increase its temperature until it reaches to a critical point. What is that critical point? That critical point is its freezing or melting point. So this is the melting point because it is going to start to melt at this point. And the energy that you give during this part is going to be basically used to change the temperature. So then you basically use MC delta T equation to calculate, or the relationship in between the heat given to the system is going to change the temperature, and the relationship is as follows: MC delta T is equal to the Q. But if you are at that critical point, which is melting or freezing point, then in this region, what's going to happen, you are going to use the energy at a different purpose. At this point, you're going to use the energy to rearrange the molecules, because at this point A, you are solid. But once you are here, you are liquid now. So that's why in this region, at region B, you are not going to use energy to change the temperature, but rearrange the molecules. So basically the quantity for that is called latent heat. So, and this latent heat is basically energy needed per mass to move them from one place to another. So heat given in this part will be used to reorganize the molecule and change the phase from solid to liquid. And if you're at C, then again, you're using the energy to change the temperature. But if you again come to a critical point, which is boiling, then you use this energy to change phase again, and you are going to basically use the equation of ML. All right, so that is basically how heat is used at different sections of objects when they're changing, when they're added heat to them. All right, so that is basically the summary of heat and energy transfer. So thank you for watching.